Today's lecture is related to 2 by 2 system of linear congruence. So this is lecture 5 of the lecture series. So for example, we have a system AX plus BY congruent to E modulo M, and the second congruence is CX plus DY is congruent to F modulo M. Okay, so this system has a solution in the form of linear congruence, or in the form of X congruent to X null modulo M, and Y is congruent to Y null modulo M. Okay, so these two congruences satisfies both of the congruences. Okay? So not all 2 by 2 systems of linear congruences are solvable. So we have a result. Okay, so by using that result, we can find whether the system is solvable or not. Okay, so there is a result theorem. The statement is the linear system AX plus BY is congruent to E modulo M, and Cx plus dy congruent to F modulo M. Okay, this system has a unique solution, if and only if GCD of delta and M is 1, where delta is the determinant of the coefficients of X and Y in the system. So delta is congruent to the coefficient or determinant of the coefficients AD minus BC modulo M. Okay. Okay, now look at the proof. Suppose, so this condition is with if and only if. So we suppose this system has a solution X is congruent to X null modulo M, and Y is congruent to Y null modulo M. If X null and Y null are the solution, or these two congruences are the solution of this system, so it means they must satisfy uh, uh, the above system, or you can call them equation 1 and equation 2. Okay, so system 1 and 2 implies, so we put x null and y null here in equation in congruence 1 and 2. So this will become ax null plus by null congruent to E modulo M, and Cx null plus dy null is congruent to F modulo M. Okay. Now we can solve these two congruents simultaneously. We call this congruence as 3 and this one as 4. Okay. Now if we multiply B in congruence 3 and B in congruence 4. Okay, so that the coefficient of y null becomes same, and we will be able to find the value of x null. So congruence 3 becomes a dx null plus b dy null congruent to dE modulo M. Congruence 4 implies BC x null plus BD y null congruent to BF modulo M. Subtract these two congruences. So here we will get negative signs, these two terms cancelled, then we will have AD minus BC times x null congruent to DE minus BF minus BF modulo M. Okay, so we have this linear congruence. Okay, and we know that this linear congruence is solvable if and only if the GCD of coefficient of x null and M is 1. Okay, so x null has unique value if and only if and only if GCD of AD minus BC comma M is equal to 1, and we know that this AD minus BC is delta, so GCD of delta and M is 1 within if and only if condition, and that's the required condition. Similarly, you can form equations for y null. Okay, so the above system, similarly you can form for y null. Okay, So the above system has a unique solution if and only if GCD of delta and M is equal to 1. Okay. And now we have a very important next result, okay, that gives you the procedure that how to solve 2 by 2 system of linear congruence. Okay. So next result, when the statement, when the linear system when the linear system ax plus by congruent to E modulo M and Cx plus dy congruent to F modulo M has a unique solution modulo M, okay, and this solution is given by solution M. It is given by X null is congruent to delta inverse ED minus BF modulo M and Y null congruent to delta inverse ED minus BF modulo M, where we know that where delta is congruent to AD minus BC modulo M and delta inverse is the inverse of delta over the modulo M. So that's the statement of the theorem. So by using that theorem, you can easily or you can directly find the value of x and y, okay, just taking the inverse of the determinant. So it means the determinant must be invertible. Okay, look at the proof. We know that it's given here the system has a unique solution. Okay, so it's given here the system has a unique solution. So we know that if the system has a unique solution, so according to previous theorem, we have the GCD of the determinant of the coefficients and M is always 1. So we can write the system has a unique solution modulo M Thus, determinant of delta and m must be equals to 1. GCD of determinant and m is equal to 1. So, delta is invertible. Invertible, okay, modulo m. Okay, because we know that the solution exists and the solution is unique. So we just need to find the solution. Okay. So, for example, we assume that let x null and y null be the solution of the given system. Okay. So if x null and y null is the solution of the given system, then ax null plus by null, okay, congruent to e modulo m, and cx null plus by null congruent to f modulo m. And we apply the same procedure that we applied in uh, in the previous example. Okay, so previous theorem. Okay, so by applying the same procedure of theorem. For example, you can call this theorem as theorem 5, and you can call this theorem as theorem 6. Okay, so by applying the same procedure of theorem 5, okay, means we multiply first congruence by D and second congruence by B, and then subtract, we will get AD minus BC times X null. Okay, so thus we will have AD according to the previous example that we discussed here, AD previous theorem, AD minus BC times X null. So we will have AD minus BC times X null is congruent to, the next thing is DE minus BF, DE or ED, whatever. So DE minus BF times modulo M. Okay. So since GCD, you can write AD minus BC as delta. So this will become delta X null is congruent to DE minus BF modulo M, and delta is invertible. So because delta inverse exists here, so delta inverse delta X null is congruent to delta inverse times DE minus BF modulo M. So this gives you 1. 1 times x null is congruent to delta inverse ED. Okay, you can write ED as well. ED minus BF times modulo M. Okay, so that's the required thing for, or the required solution for x null. Okay, so here we have value of x null. Similarly, if we multiply by C in congruence 3 here, and by A in congruence 4, and then subtract, we will be able to find the value of y null, and that will be same as which is given here. Okay, let me try to solve this. Okay, for example, you can call this as 5, this one as 6. So multiplying 5 by C and 6 by A, now 5 becomes AC x null plus BC y null. Okay, or sorry, we are not multiplying C and A here in 5 and 6. Okay, because we have variables here, so it's better to name 5 and 6 here. 5 and 6. Okay, so if we multiply 5 by C and 6 by A. Okay, because we need x null and y null, and we have variables here, so it's better to use 5 and 6 here from here. So congruent EC modulo M, and 6 implies AC times x null plus BC, no, sorry, times, we are multiplying by A, so AB y null. Okay, I think I made a mistake here. It's D, not B. It's D. So this will be BD. This must be BD. D and A. So AD. AD congruent to AF modulo M. Okay. Now subtract. Subtract two congruences. Cancelled. Now here we have BC minus AD times y null, which is congruent to EC minus AF modulo M. Okay, and BC minus AD can be replaced by delta because this is the determinant of the coefficients of x and y in the system. So delta y null is congruent to EC minus AF times modulo M. Okay, now we know that delta is invertible, so we multiply by the inverse of delta both the sides of the congruence, so we get y null is congruent to delta inverse EC minus AF modulo M. Okay, That's the required result uh, for the second one. Uh, Actually, I made a little bit mistake here in the writing of the statement. So this value should be corrected, and this is EC minus AF. Okay, that we got here. EC minus AF, or sometimes we can write AF minus EC, whatever. Okay, so that's the required result. So by using this result, we can easily, that's the proof of the theorem. So by using theorem, or so result can be written as, okay, that's the proof of the result. So you can write x is congruent to x null, because x null and y null are the solution, modulo m, and x null is actually uh, x null is delta inverse ed minus bf modulo m. Similarly, y can be written as y congruent to y null modulo m. So by using this result, any system of 2 by 2 linear congruence can easily be solved in 2 steps. Okay, just 2 steps. For example, consider a very simple example here. Okay, an example. So we have a linear system. So 3x plus 13y congruent to 8 modulo 8 modulo 55, and 5x plus 21y is congruent to 34 modulo 55. Okay, so we are able to find delta modulo 55. Okay, so we will see that whether this is solvable, or whether this system has unique solution or not. So first we need solution. So first we need to find the value of delta. So a b c d. So ab, okay, ad minus bc. So 3 times 21 minus 13 times 5. Okay, better to write congruent, and this is congruent to 23 times 21 is uh, 3 times 21 is 63, and 13 times 5 is 65. So this is minus 2 modulo 55. So minus 2 is 53 modulo 55. Okay, so delta is 53 here, and m is 55. So we take GCD of 53 and 55, 53 and 55, because we need GCD of delta and m, which is 53 and which is 1. So it means the system has a unique solution modulo 55. So the system has a unique solution modulo 55. Okay, now so x null will be equal to, okay, and what about the delta inverse. Okay, so we have to find a number which should be multiplied by 53 and gives you 1 in modulo 55. Okay, so because x null, if we look at the formula for x null, so x null is delta inverse ed minus bf. So this is delta inverse ed minus bf modulo m. Okay, so what is a here? This is a, b, c, d, e, and f. This is e. Okay, so ed minus bf. So ed minus bf is 21 multiplied by 8 minus bf 13 multiplied by 34. Okay, and we have to find this value for modulo m. Okay, so and what will be the value of delta inverse? So we need to find a number which can be multiplied by 53 to get 1. So 53 is delta, then the other number will be delta inverse. Okay, so that number you might need a calculator here. So that number is 27. So if you multiply 53 by 27, you get 1431. Okay, and 1430 is divisible by 55. So it means this gives you 1. So delta inverse is 27 here. Okay, now x null is congruent to 27 times 21 times 8 minus 13 times 34, and this is congruent to 21 times 8 minus 13 times 34, and this is congruent to 27 modulo 55. Okay, now look at the value for y null. Y null is congruent to delta inverse EC minus AF, or whatever, AF minus EC, there is no difference. So delta inverse EC minus AF times modulo M. So Y null is congruent to delta inverse is 27 EC minus AF. So 5 EC, C is 5 times 8 minus AF. So 3 times 34, which is congruent to 24 modulo 55. Okay. Now the two congruents, or the two solutions are, so thus x is, because we have 27 here and we have 24 here, so x null is 27 and y null is 24, so we can write x is congruent to 27 modulo 55, and y is congruent to 24 modulo 55. Okay, so that's the solution of the 2 by 2 system of congruences. Okay, now that's the end of the topic of linear congruence, and we will revisit this topic. We will revisit congruence with quadratic congruences, and before studying quadratic congruences, we will study the three famous results. One of them, Wilson's theorem, the other one is Fermat's little theorem, and the third one is the Euler's theorem. Okay, so these three theorems or these three results are very important. So we will study those theorems, and then we will move towards multiplicative functions or number theoretic functions. Okay, so more on number theoretic functions. Then we will study quadratic congruences. Okay, so our new topic is the Wilson's theorem. Okay, so before going to the proof of Wilson's theorem, let me uh, let me introduce a lemma before going to the statement of Wilson's theorem. So lemma, you can call it lemma 1. Okay, a positive statement is a positive integer a is self-inverse or self-invertible. It's better to use the word self-invertible. Self-invertible modulo p if and only if and only if a is congruent to plus minus 1 modulo p. Okay, so it means if a is any integer for modulo any integer which is self invertible means for example the inverse of a is a for modulo p. In that case there are only two possibilities of a, 1 and minus 1. Okay, let's move to the proof of the lemma. Okay, so because this theorem has if and only if with has if and only if condition, so we have to prove it in both ways. Okay, so first we suppose a is self invertible. Okay, suppose a is self invertible. So if it is self invertible, it means is inverse is same. It means the square of that number is 1 because it's self invertible. So then a square is congruent to 1 modulo p. Okay, so by using the definition of the congruence, if a square congruent to 1 modulo p, it means p divides a square minus 1. So implies p divides a square minus 1. So if p divides a square minus 1, it means p divides two factors a minus 1 times a plus 1, because uh, p is prime. Okay, you cannot make factors of p, so it means and p is dividing a square minus 1, which is factorizable, and you can make two factors of that. So it means p either divides a minus 1 or a plus 1. So this implies p divides a minus 1 or p divides a plus 1. Okay. So if p divides a minus 1, so this can be written as a is congruent to 1 modulo p, and if p divides a plus 1, it means a congruent to minus 1 modulo p, and that's the required condition. A is congruent to plus minus 1 modulo p. Okay. Now move to the converse of this result. Conversely, conversely, assume that a is congruent to plus minus 1 modulo p, plus minus 1 modulo p. Okay. So if a is congruent to plus minus 1, so a is congruent to 1 modulo p, or a is congruent to minus 1 modulo p. In both of the cases, in both cases, a square is if we square here and if we square here, so in both cases a square is 1 modulo p. This gives you, so a is self inverse. Self invertible, sorry. Self invertible modulo p. Before moving to Wilson's theorem, okay, let me illustrate Wilson's theorem by using an example. Okay, for example, uh, we have 10 factorial. Okay, so find the remainder when 10 factorial is divided by 11. Okay, so this 10 factorial can be written as 11 minus 1 factorial, and 11 is a prime number p. Okay, so now look at the look at 10 factorial. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, I have written all of them. Now we are dividing this by 11. Okay, okay, so we should make pairs so that the result is 1, or the two numbers which are, because 11 is a prime number. So Z11 is a field. So by definition, every non-zero element of Z11 means every element from 1 to 10 has an inverse. Okay. So we have to pick those numbers which are inverse to each other. Okay, for example, look at 6 and 2. Okay, 6 times 2 is 12, which is 1 when divided by 11 or in Z11. Okay, so let me write, okay, 1 times 1 is 1, okay, because the inverse of 1 is 1. It's a self inverse, okay, and 6 times 2 is 12, which is 1 again. 6 times 2, okay, 6 times 2 is 12, which is 1. Then we can arrange 4 and 3. So 4 times 3 is again 12, which is 1 when divided by 11, okay, or modulo 11. Okay, so we considered, so let me use a different color. We consider this one, we consider this one, and we consider 9 times 5. 9 times 5 is 45. So 45 is 1 because 9 and 5 are inverse to each other. So 9 times 5. And now we have 8 times 7, 8 times 7, and then 10 because the inverse of 10 is 10 again. So there are only two numbers which are inverse, which are self inverse. The first one is 1 and the other one is 10. Okay, so let me use congruent sign, congruent, okay, congruent to modulo 11. So this is 1, this is again 1, this is again 1, 1, 1, and we have only 10 here. 10 modulo 11, and this 10 can also be written as -1 modulo 11. Okay, so here in this example, we have seen that there are only two elements which are self-invertible. Okay, one is 10 and the other is 1 when we are having modulo 11. Okay, and by using this technique we can find the remainder when divided by some prime. For example, we took it here 11. Okay, now move to Wilson's theorem. So by using Wilson's theorem, you can solve this example in one step. Okay, so this is Wilson's theorem. The statement is, if P is a prime, then P minus 1 factorial is congruent to -1 modulo P. Okay, so look at here. So P in this example, okay, the example which is given here, uh, 10 is, P is 11, and 10 factorial means 11 minus 1 factorial. So this is just equal to -1 modulo 11. Okay, by using the statement of Wilson's theorem, you can solve this type of example or these types of problem just one steps. Okay, now move to the proof of Wilson's theorem. Okay, when p is equal to 2, the, the proof is trivial because p minus 1, so 2 minus 1 is 1, factorial is congruent to -1 modulo 2. Okay, so thus the theorem is valid for p is equal to 2. Let p is greater than 2. Okay, so now we are considering any prime which is greater than 2, and we know that by using the lemma above or lemma 1, then then only two integers are self-invertible when we take modulo p or over the modulo p. So if we have p is greater than, if we have p greater than 2, then there will be two positive integers which are self-invertible modulo p. Okay, then, and those were the first and the last. Okay, because if you consider zp as a field, okay, so zp is a field, so 1 2 3 till p minus 2 p minus 1. Okay, so 1 and p minus 1 are self invertible, so p minus 1 can also be written as -1. Okay, so then 1 and p minus 1 are self invertible modulo p. So it means there is no role of 1 and p minus 1 when divided by p, because the remainder will remain 1 or -1. Okay, so then we consider the remaining elements from 2 to p minus 1. Okay, so we consider remaining elements, and we know that every non-zero element of if of zp has an inverse. So the inverse of 2 must exist in zp as well, and similarly inverse of 3, similarly inverse of p minus 2. So every element of every non-zero element except 1 and okay, I forgot to write 0 here, because this is a field and there must be a 0 in the field as well, although we are not considering 0 here, but we should include 0 here as well, but we are not considering 0. Okay, so p minus 1 factorial is congruent to 1 times, okay, then 2 times 3 times till p minus 3 times p minus 2 times p minus 1 modulo p. Okay, as we discussed that p minus 1 is minus 1 modulo p, and all the remaining non-zero integers of zp except 1 and minus p has their inverses. Okay, so in from 2 to p minus 2 there must be an inverse of 2. Okay, in the same product. Okay, so if we write those integers in pairs, so we will get 1 in the form of products. Okay, so at the end if we write these numbers in the products, so at the end we will get 1. So at last we will get 1 as the product here. So 1 times p minus 1 modulo p, and this gives you minus 1 modulo p. That's the proof of Wilson's theorem. Thank you very much. Allah Hafiz.